Welcome to Lesson 4.3, Configuring Training Parameters. Overview. Training parameters can make or break your fine-tuning results. Too high learning rate? Model diverges. Too small batch size? Training takes forever. In this lesson, you'll learn to configure training parameters optimally for your Tesla P40 GPUs. Duration: 45 minutes. Difficulty: intermediate. Learning objectives. By the end of this lesson, you will understand key training hyperparameters, choose optimal learning rates, configure batch sizes for Tesla P40, set up gradient accumulation, configure warm-up and learning rate scheduling, enable memory-efficient training on Windows, set up logging and checkpointing. Key training parameters. This script is designed to fine-tune a language model using the Unsloth library, and it consists of several key steps. First, it imports necessary libraries and initializes the model by loading a pre-trained version of Llama 3.2 3B instruct, setting it up for 4-bit loading to optimize memory usage. The script confirms successful loading with a message. Next, LoRa adapters are added to the model, which enhance its ability to learn from specific tasks without requiring extensive resources. This is crucial for efficient fine-tuning. The script then prepares the training and validation datasets, loading them from JSON files and applying a chat template to format the input correctly. It outputs the number of training and validation examples, ensuring your data is ready for training. After configuring training parameters with training arguments, the script creates an SFT trainer instance, which encapsulates the model, tokenizer, and datasets for training. Finally, it checks GPU properties and starts the training process, monitoring the loss to ensure it decreases over time. Once training is complete, it provides metrics like training time and final loss, confirming the training's success. This code snippet is essential for verifying your environment setup before loading models with Unsloth. First, it imports the necessary libraries, specifically Fast Language Model from Unsloth and PyTorch. The next 3 print statements provide crucial information about your PyTorch installation. The first output confirms the version of PyTorch you're using, which is important for compatibility with Unsloth. The second line checks if CUDA is available, indicating whether you can leverage GPU acceleration for faster processing. Finally, the third statement retrieves the name of your CUDA device, which lets you know the specific GPU being utilized. Seeing CUDA available, true, and the name of your GPU, like Tesla P40, confirms that your environment is set up correctly for efficient model training and inference.
Sometimes you don't want the final checkpoint, you want a specific point mid-training. Maybe your validation loss was lowest at step 100 before it started creeping back up.
This code loads that exact snapshot by pointing from pre-trained at the step 100 subdirectory inside your checkpoint folder. Everything else is identical to a normal load. Max seeks length 2048, load in 4-bit jugaing, then for inference to activate prediction.
The confirmation message tells you that specific checkpoint is live. This technique is how you recover the best version of your model even if you let training run too long.
Creating test cases.
Good evaluation doesn't happen with one example. It happens across a deliberately varied set of cases.
Each test case here is a dictionary with 3 fields, a human-readable name so you know what you're testing, an input sentence the model has never seen, and a list of fields you expect to find in the output.
Notice the variety. One case is a clean, simple sentence. Another is complex with multiple attributes. Another has ambiguous or incomplete information. That spread matters. A model that aces the easy cases but chokes on edge cases isn't production ready.
These test cases are your truth table. They tell you exactly where the model is solid and where it needs work.
Testing function.
The test model function is the core of your evaluation loop.
It takes a raw user prompt, wraps it in the Llama 3.1 chat template using getChatTemplate, tokenizes it, runs it through the model, and then decodes only the assistant's reply, stripping the prompt back out of the output.
Temperature is set to 0.1, which keeps the model focused and deterministic rather than creative. That's exactly what you want for structured extraction tasks, where you need consistent JSON output, not creative variation.
Run this with a sample prompt and confirm the output is clean, correctly formatted JSON before you move on to batch testing.
Training time estimates.
To know whether fine-tuning actually helped, you need a reference point. This code loads the original Unsloth Llama 3.2 3B instruct base model, the same weights your fine-tuned model started from, as a separate object called base model.
The parameters are identical. Max EXU length will 2048, load in 4-bit Jugain, and 4 inference to prepare it for prediction. Having both models loaded simultaneously lets you run the exact same prompt through both and see the difference directly.
Without this comparison, the model works is just a feeling. With it, improvement becomes a measurable fact.
The compare models function runs the same prompt through both models and prints their outputs side by side.
For the base model, it tokenizes the prompt directly, sends the tensor to the GPU, generates up to 200 new tokens at temperature 0.1, then decodes and strips special tokens from the result.
For the fine-tuned model, it delegates to your test model function. The side-by-side print is intentionally simple. You want to read both outputs in one glance and immediately see whether fine-tuning changed the behavior.
That visual diff is often more revealing than any numeric metric.
Here's what that difference typically looks like. The base model tends to be verbose and inconsistent. It might describe what it's doing, add caveats, or return the data in a format you didn't ask for.
This is a representative base model response to a structured extraction prompt. Notice it's not returning clean JSON. It's narrating the extraction process in natural language, identifying name, age, profession, and workplace as pros.
That's the base model doing what it was originally trained to do, generate helpful text. It hasn't learned your specific output contract. The information is technically correct, but it's in the wrong shape for any downstream system expecting JSON.
This is exactly the problem fine-tuning is meant to solve.
A fine-tuned model, by contrast, should return something tight and machine-readable.
This is the target output, a clean JSON object with exactly the fields you asked for: name, age, occupation, and company. No preamble, no explanation, no trailing text.
The fine-tuned model has learned the output contract from your training data and applies it consistently. When you see this kind of output from your model, it confirms that fine-tuning transferred the right behavior.
If your fine-tuned model is still producing prose like the base model did, that's a signal to revisit your training data formatting or add more examples.
Analyzing training metrics.
Your trainer saved a trainerstate.json file inside every checkpoint directory. That file contains the full log history, every loss value recorded during training.
This code opens that file, walks through the log entries, and splits them into two lists: training loss values keyed on step count, and evaluation loss values keyed on the steps where validation ran.
The final print tells you how many data points you have for each. More evaluation points means a finer-grained picture of how generalization evolved across training.
If that number is 0, your evaluation dataset wasn't configured. Go back and check your training arguments.
This output shows the evaluation loss for each epoch during your model training process. The evaluation loss is a critical metric that helps you understand how well your model is performing on unseen data. In the first epoch, the loss is 1.5, which is relatively high, but as you progress to the second and third epochs, you see a decrease to 1.2 and then 1.1. This indicates that the model is learning and improving. However, in the fourth epoch, the loss slightly increases to 1.15, which is a warning sign that the model may be starting to overfit the training data. By the fifth epoch, the loss rises further to 1.20, confirming that overfitting is occurring. At this point, it's crucial to stop training to prevent the model from memorizing the training data rather than generalizing well to new data. Monitoring these loss values helps ensure you achieve a balance between training and validation performance.
This is the output you want to see.
Training loss drops from 3.0 to 0.6 across epochs, and validation loss tracks it closely, falling from 3.1 to 0.7. The key signal here is that both curves move together.
Validation loss staying close to training loss means the model is generalizing, it's learning the underlying pattern, not memorizing specific training examples.
Watch for the moment those two curves diverge. If training loss keeps dropping while validation loss flattens or rises, you've crossed into overfitting territory and should consider stopping at an earlier checkpoint.
That pattern, both losses decreasing together, is the diagnosis of a well-trained model. If your curves look like this, you're in good shape. Now look at what the problematic patterns look like.
This line of code sets the optimization algorithm to AtomW 8-bit. Using AtomW with 8-bit precision is essential for fine-tuning large language models efficiently, as it reduces memory usage while maintaining performance. This is particularly beneficial when working with limited resources or larger datasets. By specifying this optimization method, you're instructing the training process to leverage the advantages of 8-bit computation, which can lead to faster training times and lower memory consumption. It's a practical choice that balances performance with resource constraints, ensuring that your model can learn effectively without overwhelming your system. Benefits: 75% less memory than regular AtomW. Minimal quality loss. Works great on Windows. Perfect for Tesla P40.
This is the undertraining signature. Training loss only drops from 3.0 to 2.6. And validation loss barely moves from 3.1 to 2.7. Both numbers are high, and neither is improving meaningfully. The model hasn't learned enough.
This could mean you need more epochs, a higher learning rate, a higher LoRa rank to give the model more capacity to learn, or a closer look at your dataset. Noisy or inconsistently formatted training data produces exactly this kind of plateau.
The remedies for undertraining are the mirror image of overfitting fixes. Train longer, raise the learning rate, increase LoRa rank, or improve data quality.
The loss curves tell you which problem you have, then you know exactly which lever to pull.
Quantitative evaluation.
The batch test function runs your entire test suite through the model in one pass.
For each test case, it constructs the extraction prompt from the input field, calls your model function to generate an output, and packages the result, name, input, output, and expected fields into a results list.
After the loop, it prints every result in a structured format so you can scan all inputs and outputs at once. This batch view is what separates rigorous evaluation from cherry-picking a single impressive example.
The score output function gives you a numeric handle on what you're seeing qualitatively. For each expected field in a test case, it checks whether that field name appears anywhere in the model's output, case insensitively.
It counts the matches and divides by the total number of expected fields to produce a percentage. The loop then prints that percentage for every test case.
This isn't a perfect metric. A field name appearing in the output doesn't guarantee it has the right value, but it's a fast, practical signal for whether the model is producing the right structure.
Use it to triage, then read the actual outputs for the cases that score low.
This output shows your model scoring in the high 80s and 90s across all test cases with an average of 91%. That average is the headline number, but the per-case breakdown is where the real information lives.
A case scoring 60% while others score 100% tells you exactly which scenario needs more training examples.
A uniformly high score across simple and complex cases alike means your model has genuinely learned the task, not just the easy version of it.
Qualitative evaluation.
Quantitative scores tell you how often the model gets it right. Qualitative evaluation tells you how it fails when it gets it wrong.
This JSON dataset, 3 people with names and ages, is the kind of ground truth you feed into a qualitative check.
You know exactly what the correct output should look like for each entry, which means any deviation is immediately visible. Structured ground truth like this is what makes qualitative evaluation systematic rather than impressionistic.
This code snippet sets up the training parameters for fine-tuning your language model using the training arguments class. The output dir specifies where your model outputs will be saved, which is crucial for organizing your results. The max steps is set to 50, indicating a very short training duration, suitable for quick tests or debugging. The per-device train batch size of 4 defines how many samples will be processed at once on each device, balancing memory usage and training speed. The learning rate of 2E4 is a standard starting point for many models, while warm-up steps at 5 helps stabilize training initially. Logging every 10 steps allows you to monitor progress without overwhelming your output. Both eval strategy and save strategy are set to no, meaning no evaluation or checkpoints will be created during this run. Finally, using AtomW 8-bit optimizes memory usage, and enabling FP16 allows for faster training with reduced precision. This configuration is tailored for quick experimentation, ensuring you can iterate efficiently.
The cleanest output is the one that contains exactly what you asked for and nothing else.
When the model adds commentary around its JSON, explaining what it found, or narrating its reasoning, that's a format failure, even if the embedded data is correct. A downstream parser will break on that extra text.
This is the ideal output. A bare JSON object, no preamble, no trailing explanation. Just Dane name John, age 45. Every character is load-bearing.
This is what your training data should have taught the model to produce, and seeing it here confirms the format contract was learned.
When you're doing qualitative review, this is the bar. Anything with extra text around the JSON is a partial failure, even if the score function gave it full marks.
Use for production models, critical applications, Windows-specific settings. This code snippet configures essential training parameters for fine-tuning your model with unsloth on Windows. First, it sets the optimizer to AtomW 8-bit, which is efficient for memory usage and helps speed up training without sacrificing performance. Next, it specifies the use of FP16, or half-precision floating point, which is particularly beneficial on the Tesla P40, allowing for faster computations while still maintaining model accuracy. Note that BF16 is set to false here, as it isn't supported on this setup. Enabling gradient checkpointing is also crucial. It saves memory by storing only a subset of intermediate activations during the forward pass, which can significantly reduce memory usage during training. The comment about flash attention highlights that it's not available on Windows, so we won't be using it here. Lastly, the data loader workers are set to 0, or a maximum of 1 or 2, which is a practical choice on Windows to prevent potential performance issues. Adjusting these parameters ensures a smoother training process tailored to your environment. Unsloth automatically handles most Windows quirks. Testing configuration.
The first retraining signal is inconsistency. The model produces correct output on some inputs and wrong format on others, seemingly at random. That's not a data problem, it's a training duration problem.
The model learned the pattern but hasn't reinforced it enough to apply it reliably. The fix is more epochs or more training examples that demonstrate the correct format.
The second signal is a validation loss that's more than 0.5 higher than training loss. That gap is the overfitting indicator. The model has started fitting to the specific examples in your training set rather than the general pattern.
Your best move is to load the checkpoint where validation loss was at its minimum, not the final weights. If that checkpoint still underperforms, add more training data or lower the learning rate to slow down the fitting process.
Third signal is format drift. The model's outputs don't match the structure you specified in your training data. This almost always traces back to inconsistent formatting in the training examples themselves.
Check whether your training data has a uniform output structure. If some examples use one JSON schema and others use a slightly different one, the model will average across them and produce neither reliably.
Standardize the format in your training data and add more examples that demonstrate the exact structure you want.
The fourth signal is the most discouraging one. The fine-tuned model produces outputs indistinguishable from the base model. Fine-tuning had no measurable effect.
This happens when the learning rate is too low for the gradient updates to meaningfully shift the weights, when training ran for too few steps, or when the training examples weren't challenging enough to push the model beyond its default behavior.
Raise the learning rate, train longer, and make sure your training data contains examples that the base model genuinely cannot handle correctly.
Complete Evaluation Notebook.
This notebook at notebook/03firsttraining/04evaluate.ipnb pulls together everything from this lesson into a single runnable document. It loads your fine-tuned model with from pre-trained, sets max elix length 2048 and load in 4-bit dugong, then confirms
The test model function handles tokenization, generation, and decoding. A quick single prompt test runs first so you can confirm the model is responding before you commit to the full batch.
Then the batch test runs all your test cases and prints structured results. Finally, the notebook loads trainer state.json from your latest checkpoint, extracts training and validation losses, and plots both curves.
The summary at the bottom reads those curves and prints a plain English diagnosis, healthy training, overfitting, or undertraining, so you always leave the notebook knowing exactly what to do next.
What's next?
Work through this checklist before you declare your model ready. On the technical setup side, the model loads without errors, inference mode is active, and the test function returns output without exceptions.
On the quantitative side, training loss is below 1.5, validation loss is below 2.0, and validation loss is not more than 0.5 above training loss. The loss curves show a downward trend without divergence.
On the qualitative side, outputs consistently follow the expected format. The model handles your full test suite accurately, and it outperforms the base model on the comparison prompts without introducing hallucinations. If the checklist passes, save and deploy.
If it doesn't, the retraining signals from the previous section tell you exactly where to focus.
Key takeaways. 6 things to carry forward from this lesson. Always compare against the base model. Improvement needs to be measured, not assumed. Always check validation loss. Training loss alone cannot tell you whether the model generalizes.
Test diverse cases. Edge cases expose failure modes that clean examples never will. Visualize loss curves. The shape of those curves tells you more than any single number.
Manual review is irreplaceable. A 91% field match score can hide a model that's structurally broken in ways the metric doesn't capture.
And iterate without hesitation. The first training run is rarely the best one, and now you have the tools to know exactly what to change.
What's next? If your evaluation passed, continue to Lesson 4.6, where you'll save your model in formats ready for deployment and learn how to share it on Hugging Face Hub.
If your model needs work, head back to Lesson 4.3 to adjust your training configuration. You now know exactly which parameters to change and why.
Additional resources.
The course materials include links to model evaluation best practices, a guide for comparing models systematically, and a broader LLM evaluation reference covering metrics beyond what we used here. Your model is trained and evaluated.
The hard part is done. One lesson stands between you and a deployable, shareable model.
Before you run a single test, it's worth knowing what the evaluation landscape looks like, because different tasks call for different metrics, and using the wrong one gives you a false picture of performance.
Perplexity measures how confidently the model predicts the next token. Lower is better, and it's a useful general-purpose signal.
Rouge is the standard for summarization. It measures the longest common subsequence between your output and a reference, capturing both content and order. Bli-UI is the equivalent for translation, measuring n-gram precision against a reference.
Win rate is used for chat models. You run head-to-head comparisons and measure how often your model is preferred.
Task accuracy, exact match, or F1 is what you'll use most in this course because structured extraction tasks have a clear right answer. Knowing which metric fits your task means your evaluation actually measures what you care about.
A radar chart makes multidimensional comparison intuitive. Each axis represents a different capability: domain knowledge, answer accuracy, tone consistency, task completion, and others. And the area enclosed by each model's line represents its overall profile.
The fine-tuned model's line extends further outward on domain knowledge and answer accuracy, which are exactly the dimensions fine-tuning is designed to improve. Notice that the gains aren't uniform. Some axes show larger improvements than others.
That uneven shape is normal and informative. It tells you which capabilities your training data targeted effectively and which ones might benefit from additional examples.
A radar chart like this is worth generating for your own model after you complete evaluation.
The evaluation pipeline has a clear sequence. Start by identifying the best checkpoint, the one with the lowest validation loss, not necessarily the final one. Run your test set through that checkpoint to generate responses.
Feed those responses through automated metrics. Rouge scores and perplexity give you fast, scalable signal. Then add an LLM as judge step. Use a capable model like GPT-4 to compare your outputs against the baseline and compute a win rate.
Follow that with human spot checks on a sample of around 50 rows to catch anything the automated metrics missed. Aggregate everything, compare against your baseline numbers, and make the call. Deploy or continue fine-tuning.
This pipeline scales from a quick sanity check to a rigorous production evaluation depending on how many of these steps you activate.
Benchmark scores give you a standardized way to compare your fine-tuned model against the base model on tasks that have well-established reference datasets. This chart compares Llama 3.8b base against its fine-tuned version across MMLU, Human Eval, HelloSwag, Truthful QA, and GSM-8K.
The fine-tuned model scores higher on every benchmark. The green bars consistently extend further than the orange ones. MMLU tests broad knowledge, Human Eval tests code generation, HelloSwag tests common sense reasoning, Truthful QA tests factual accuracy, and GSM-8K tests math reasoning.
The gains are visible across all 5, which tells you fine-tuning improved the model broadly, not just on the specific task it was trained for.
Running your model against even a subset of these benchmarks gives you a credible, externally comparable performance number.
Rouge scores are the standard evaluation currency for tasks where you have a reference output to compare against. Rouge 1 measures single-word overlap. A score above 0.40 indicates strong content coverage.
Rouge 2 measures two-word phrase overlap, which captures more of the sentence structure. Aim for above 4.18. Rouge L measures the longest common subsequence, which reflects sentence-level coherence. Above 4.35 is the target. Rouge L sum is the summary level variant, targeting above 4.33.
Blue complement rouge for translation tasks, measuring n-gram precision rather than recall. Above 0.2 is considered meaningful. These thresholds aren't universal laws. They're practical benchmarks for knowing whether your score is in the right neighborhood.
Always interpret them relative to your specific task and dataset.
Perplexity is one of the most useful diagnostic numbers you can compute on a language model.
It measures how surprised the model is by the text it's predicting. Lower perplexity means the model finds the text more predictable, which generally correlates with better quality. The chart here breaks the range into 3 zones.
The green zone, perplexity between 1.5 and 5, is where well-trained models land. The yellow zone, 5 to 12, is acceptable but suboptimal.
Above 12 is the concerning zone. The model is struggling to predict the text, which usually means it hasn't learned the domain well. One important nuance: perplexity below 1.5 is also a warning sign.
That level of confidence often indicates memorization or overfitting rather than genuine understanding. Use perplexity as a quick health check, but always pair it with qualitative review.
The Vibe Check framework is your qualitative evaluation protocol, the structured version of does this model actually feel right? Work through 7 dimensions. Correctness. Does the model answer the question accurately?
Hallucination. Does it invent information that wasn't in the input? Test this against inputs where you know all the facts. Format. Does the output consistently match the structure you specified?
Tone and style. Does the model's voice match what you trained for? Edge cases. How does it handle ambiguous or underspecified prompts? Refusals. Is it declining requests it should handle or handling requests it should decline?
And comparison. Does it clearly outperform the base model on the same prompts? Running through all 7 gives you a complete picture that numeric metrics alone can't provide.
Your evaluation dataset is only as good as the principles behind it. The most important rule is the holdout principle. Evaluation examples must never appear in training data.
Any overlap invalidates your results.
The dataset should be representative. It needs to reflect the actual distribution of queries your model will face in production, not just the easy ones. Include challenging edge cases and ambiguous prompts because those are where failure modes hide.
Aim for 50 to 200 examples, enough for statistically meaningful metrics, not so many that evaluation becomes a bottleneck.
Once you finalize the evaluation set, lock it and don't modify it. Changing the evaluation set between runs makes your results incomparable. And always do a human spot check on 10 to 20 outputs per evaluation run.
Metrics have blind spots. Human review catches what they miss.
This radar chart adds two dimensions that the earlier comparison didn't cover: speed and safety. The fine-tuned model leads on instruction following and accuracy. Those are the expected wins from targeted training. But notice the speed and safety axes.
Fine-tuning can sometimes affect inference latency if the model's output distribution shifts significantly, and it can affect safety behavior if the training data inadvertently reinforced or suppressed certain refusals.
Neither of those effects is guaranteed, but both are worth checking explicitly. Run your model against a set of prompts that should trigger safety refusals and confirm it still handles them correctly.
And time a batch of inference calls to confirm latency is within acceptable bounds. A model that's more accurate but slower or less safe may not be an improvement overall.
When automated metrics aren't enough, human evaluation gives you the ground truth. The process has 6 steps. First, design a rubric with 3 to 5 criteria. Accuracy, helpfulness, and tone are common choices, rated on a 1 to 5 scale.
Second, prepare 20 to 50 diverse prompts that represent real usage. Third, run blind comparisons. Present outputs from both the base and fine-tuned models to raters without labeling which is which.
Fourth, assign at least 2 or 3 raters and compute inter-rater agreement. If raters disagree significantly, your rubric needs clarification.
Fifth, aggregate scores by criteria and compute 95% confidence intervals so you know whether observed differences are real or noise. Sixth, do error analysis on any cases where raters disagreed. Those disagreements often reveal the most interesting failure modes.
Document everything in a versioned JSON file so your evaluation history is reproducible.